In lesson 1.2, we're going to be looking at a concept called a limit. And in this lesson, we're going to take a look at finding limits graphically and numerically. The importance of this introductory lesson in our calculus course is to set up a very important topic that we're going to use throughout the year. And that is the topic and concept related to a limit. So again, in this lesson, we're going to take a look at what a limit is and try to determine it graphically and numerically. So, as the title of this slide implies, we're going to be looking to try to figure out what is a limit. But before we get to that question, we have to take a look back at a few things we studied in algebra to better understand what this limit idea is based upon. So first thing we have to think about back from our algebra days is how algebra looked at points. For algebra, we considered how a function is defined at specific points. There was a certain notation that we used to indicate that, amongst other ways of writing it. And that notation was called function notation. When we wrote f parentheses x, which we say is f of x, that is how we defined this idea called function notation, which was just a fancy way of saying a y value. So if we ever took that x and replaced it with, say, a 2, that would be saying f of 2, which is then implying we're trying to find the y value for the function f when x is equal to 2. Notation is going to be a really big point that we're going to kind of focus on a lot of this year in calculus. So it's good that we review this notation back from algebra, where you might not have used it as maybe precisely as it should have been used, but here in calculus we need to be very precise with the way we write stuff, and again here we need to kind of review this idea of function notation because we're going to have a new notation as it pertains to this idea of a limit. So then, what was a function? You might have had this analogy made for you in past math classes, but if you consider a function to be, say, some sort of machine, our function, of course, is usually an equation of some sort. So if you consider that equation a machine, we know that we input an x value into this machine. And then whatever that value is, as we compute that using the function, it's going to spit out a y value. And that makes sense anytime we were considering plugging in numbers into functions, especially if it was written in function notation. That x value is being inputted into our function, and then we did the arithmetic to figure out what the y value is for that particular x value. So things are going to change a little bit again as we think about this idea of a limit. All we're going to be looking at in this lesson is limits graphically. So I think, to kind of back up a moment, we need to take a look at functions graphically in terms of how we define points. So here we have f of 5 equals blank. Again, what it's saying is that we have our x value of 5 and we're trying to find the y value that corresponds to that for the function f. When you're given a graph, it's nice and simple. All we really need to do is find the x value of 5 on the x-axis and go up till we hit the graph. Once we hit the graph or touch the graph, then it's just a matter of reading off the y value on the left, and of course here you can see it's clearly 7. So not hard, but you're going to see where this is going to take us once we introduce this idea of a limit. Here in calculus we take a look at definitely different kinds of graphs that may or may not have occurred much in your previous math classes. So as you can see here, we have a plain old graph, but for some reason that dot that used to be on the graph is now off the graph, kind of floating below the function, and in its place we have a hole. So it's not a value there anymore. But this idea of finding f of 5 still works, just like in the previous problem. We need to go to our x value of 5 on the x-axis, and then look at the y value that corresponds to that on our function. And that's really the key right there. It has to be on the function. And you can see there's two potential answers we could be getting here. It looks like one is 6 and one is 4. But of course, just like I mentioned a moment ago, that hole, and that's the key word, those are called holes, doesn't exist. And of course, a solid dot is something that exists, so we would report the answer in this case to be 4 as the y value when x is equal to 5. Again, different kinds of graphs. In this case, our graph is now kind of broken into two pieces, and we still have another dot kind of floating off of the graph itself. But again, this idea of finding function values still works in the sense that we're trying to find the point on the graph when x is equal to 5. And as you can see in this case, as we go up from the x value of 5, we're going to pass through that first hole, we're going to pass through that second hole, and our graph exists at the solid dot, which is floating above at a y value of 7. So that kind of sums up, in a manner of speaking, function notation as it pertains to finding these values graphically. So what is a limit? How does calculus interpret graphs? Well, the good news is all this algebra still works. None of this function notation is going away. All of that definitely still works. But as calculus is kind of concerned with functions, we're considering a value a function approaches around a specific point, which is called a limit. So in this case, we're not really considering what's happening at the point. A limit is a y value, and that's a very important point that I would say is worth noting here. If you're computing a limit, which we'll talk about in a moment, we're really talking about a y value, just like the examples above. When we're trying to find f of 5 in the examples above, we're trying to find a y value. So a limit is the same idea in terms of the answer, in that it's a y value. But it's not how algebra considers a y value. This limit is a y value that a function is going toward as you get closer to a particular x value. In other words, the question that we're really asking is what y value is the graph approaching as we move towards an x value. There's a way we're going to kind of do this visually with the graph, but that's kind of the definition of what a limit is. And we're going to go ahead and transition into finding those limits again graphically in the next slide. Okay, so let's go ahead and try to attempt to answer this question and look at this from the point of view of calculus, which is concerning this new idea of a limit. Just to kind of be thorough here and back up to, again, our good old algebra point of view of looking at functions. If we were to try to answer the question of f of 5 here, you can see as we go up from the x value of 5, we never touch the graph because of this hole. And there is no floating dot above or below that hole. So that value would just have to be reported as undefined. F of 5 in this case would be undefined. But that's not, again, really what we're looking at. Here we want to, again, try to understand this idea of a limit by answering this question. What is f of x approaching as x approaches 5? So, again, we need to clarify this point as it corresponds to algebra. We're not asking the y value that the graph takes on at the point in question, because we already kind of mentioned a second ago that that would be undefined. What we care about is what y value is the graph approaching as we move closer to x equals 5. The way we're going to do this is with our fingers. If you take your left finger and put it on the graph to the left of 5, and if you put your right finger on the graph to the right of 5 and move your fingers closer and closer and closer and closer as you approach 5, what we're noticing is our fingers are coming together. Our fingers are coming together and getting closer and closer to that y value of 7. So that's the observation we're making here. We don't really care that f of 5 is undefined. It is undefined, but when we're looking at it from this point of view of a limit, what we're really asking is what y value are we approaching as we get closer to that x value of 5. And again, if your fingers help you out in doing that, you can put your left index finger on the graph to the left of 5, you can put your right index finger on the graph to the right of 5, and then move your fingers slowly and closer and closer and closer as you approach 5. If your fingers are coming together, we know that there's a value that we're approaching, and that y value in this case is 7. Here, if we answer the question of what is f of 5, you can see there's this solid dot up here, so we know there's a value for f of 5. But again, we're not concerned with that solid dot. We're concerned with figuring out what value is the function approaching as we get closer and closer to 5. So again, if you like to use this finger idea of putting your left finger to the left of 5, putting your right finger to the right of 5 on the graph, and moving your fingers closer and closer and closer, you'll notice in this case, again, your fingers are coming together, and both of them are coming together at a y value of 5. So again, we can make the observation that the function approaches 5 as x approaches 5. In this case, again, this idea that we're trying to understand here is what is happening as we get closer and closer to 5. Again, if you like the finger way of trying to figure out these limits graphically, what you can do is put your left finger to the left of 5 on the graph and put your right finger to the right of 5 on the graph. In this particular case, you'll notice something's happening different than the first two cases. Our fingers are approaching 5 from the left and the right, but unlike the first two examples, they're not coming together. In this case, our left finger looks like it's approaching about 6. Our right finger looks like it's approaching somewhere a little over 4. But really the thing we need to take away from this is that the function is not approaching any particular value. There's kind of a contradiction between our left finger and our right finger, and because of that, there's no particular value that our function is approaching as we get closer and closer to 5. So that's really the idea behind a limit. Unlike algebra, where we look at the value at an x value, we're looking at what the value is as we approach an x value. And just like algebra, there's a shorthand way of writing this. Function notation is the way we wrote things in algebra. Here there is something called a limit notation. And I think it's pretty intuitive. Of course, the LIM is abbreviated for limit. This x with the arrow and the 5 is really just telling you that x is approaching 5, as you can see in the 3 examples above. So when we take a look at this notation, if we were to translate this into English, if we were to see it, what it's saying is that the limit as x approaches 5 of f of x. So this notation is really useful because instead of writing this whole long sentence out like you see in these 3 examples, we can take all of this and shorten it up a little bit. So because of that, let's go ahead and write each of these 3 examples in terms of limit notation. So luckily the function in all 3 examples is labeled as f of x. So all we need to do is write the limit as x approaches 5 of the function f of x, and that's equal to 7. Every time we write this, you can always read it that way. This is probably the first time in a math class where you really need to approach the notation as learning a new language. Anytime we see this math notation, we can always translate it into English to try to better understand it. And again, we would read this as the limit as x approaches 5 of the function f of x is equal to 7. Same thing goes for the second example. We can write all of our limit notation down and then put is equal to 5, since that's the y value we found from the graph. In the last case, since there's no particular value our fingers are approaching, no particular y value I should clarify that our fingers are approaching, we can say that that limit equals d and e. You're more than welcome to write out the 3 words of does not exist, but when something isn't defined in this limit world, we usually write down the answer as does not exist, or d and e. Okay, so I hope those 3 examples plus the introduction of that limit notation gave you a good grounding in what it is to take a limit graphically. Of course, there are more examples we're going to look at, but before we take a look at some of the more graphical examples, we can do this same idea numerically, which is just another way of saying looking at a table of values. If you consider this table of values to be the same as a graph, then really we just need to apply what we learned in the graph version to this table of values. So you can see in the top row we have select x values, and in the bottom row we have all the y values that correspond to those x values. So again, just remember that this function notation right here is just another way of saying y. So again, we know all these values in the bottom row are y values. And if you think back to the idea of a limit, we don't care that at 1.9999 the y value is 0.999. Or say the value at the very end, at 2.25 the y value is 1.25. What calculus is concerned more about is what is the y value approaching as we get closer to an x value. And you can see up here in this particular problem, if we read this limit notation, what this is asking us is to find the limit as x approaches 2 for this equation right here, x squared minus 3x plus 2 over x minus 2. Now, we could have graphed this. I could have easily put a graph, and then we could have approached this problem just like we did with those 3 previous ones, where we put our left finger on the graph, where we put our right finger on the graph, and see what's happening. Well, in a sense, this table is giving us that ability. If we think about approaching 2 from the left, and if we think about approaching 2 from the right, if we had that graph, we would be able to see visually if our fingers were coming together. And of course, if they were coming together, that y value would be the limit. Well, you can kind of clearly see here to the left of 2, we're starting at 0.75 to 0.9 to 0.99 to 0.999. If we follow that pattern, it looks like we're getting closer and closer to 1. To the right of 2, it looks like we're going from 1.25, dropping down to 1.1, 1.01, 1.001, and you can imagine that pattern continuing, and it looks like it's going to drop down to a value of 1. So if we again use that analogy from the graphs from a moment ago, it looks like our left finger is approaching 1, it looks like our right finger is approaching 1. So because of that, we can conclude, using the limit notation, that the limit of this rational expression here is equal to 1. So again, this idea of a limit is really important, that you really kind of separate that from this idea of algebra. We don't even know what the y value is. We could compute it possibly if we tried, but maybe not if you look at the details up here, but we'll talk about that in later lessons. But theoretically, we don't really care about what the y value is at 2. All we care about is what is the function approaching, what y value is the function approaching as we get closer and closer to 2 from the left and from the right. And again, in this case, it looks like the y values are approaching the value of 1. So again, we can conclude that the limit is equal to 1. Back to our graphical approach, and as we proceed through this year, you are going to see plenty of real AP examples. And this is the very first one you're going to see, a real AP test question from the past. And even with just a little bit you've learned already about limits, we can already tackle our first AP test question. So what's going on in this question? We have the graph of a function f, as shown in this figure, and we want to find which of the following statements are true. And again, other than choice A, all of these deal with this new idea concerning a limit. So let's go ahead and get choice A out of the way first. Does the y value at x equals A equal 2? That's what this function notation is asking you. What is the y value when x is equal to A? Well, in this case, they're saying it's equal to 2. And if we take a look at our graph right here at A, as we go up from A, we're going to hit a hole here. And I guess technically we don't really hit the hole because it's not a part of the graph. Since that point is not defined, we would say that that's false. Technically, f of A should be equal to undefined. So now let's go ahead and take a look at choice B. Does the limit as we approach A not exist? Well, if we take our left finger to the left of A and get closer and closer to A, and we take our right finger and put it on the graph and get closer and closer to A, you'll see that our two fingers are indeed coming together, and they're coming together at a y value of 2. So that certainly is not true. We know that the limit here does exist, and it's actually the value of 2. So let's take a look at choice C. In choice C, you can see that we're trying to figure out what the limit at B is. Well, again, we can take this idea of putting our left finger to the left of B, on the graph, of course. We can take our right finger and put it to the right of B on the graph, and it's a different part of the graph, I suppose, because we have this little jump here. And as we bring our fingers together, you'll notice our left finger looks like it's reading off a y value of 2, and our right finger looks like it's reading off a value of 1. Because those two do not match, we would have to say in this case false, because our fingers are not coming together. If our fingers aren't coming together, that answer would have to be D and E, and here they're reporting that the value should be 1. You can see now D would be the true one. Back when we were looking at choice B, we discovered that the limit at A, as we move our left finger closer to A and our right finger closer to A, we're getting close to the y value of 2, even though the point is undefined. Again, that's the distinction between the algebra way and the calculus way. So I'm just going to make these little notes here that our fingers are coming together in this case. And then of course in the last one that has to be false because of what we did in choice C. We knew that that value should be D and E because our fingers are not coming together. So of course the final answer here we can report is answer choice D. Okay, now to wrap up this lesson, let's take a look at the certain ways that a limit can fail to exist. Again, we're doing this from the point of view of looking at a graph, so don't get too wrapped up in why this function gives you this graph and all the other examples. We'll definitely take a look at that. It's definitely something you should know from previous classes, but really let's just focus on this idea of what is a limit, and when we take a limit with a graph, why would it fail to exist? Well, in this particular case, you can see if we're trying to take the limit right here with this notation, which is saying the limit as x approaches 3 of this function, which is graphed to the left, what would be the value of that? Well, again, if you use this idea of using your fingers, we would put our left finger to the left of 3 on the graph. We would put our right finger to the right of 3 on the graph. And as you move your finger closer and closer to 3, you'll notice that our fingers are definitely not coming together, and in a sense, they're just totally going in opposite directions. So we can make the observation here that the function does not get closer to a particular value. Thus, we can say the limit does not exist. Or if you want to keep it short, we can just say that all of this limit notation here is equal to D and E. And again, this is all based on this idea of us not really caring about what the value of the function is at 3, but what's happening as we approach the x value of 3. In this particular case, a little vocabulary that we're going to use definitely throughout the entire year. Whenever we have a graph that's not quite connected, we call that a jump discontinuity. When the limit approaches different values from the right and the left, we know that that's some sort of jump. So in this particular case, you can see again this limit notation is indicating that we're trying to find the limit as x approaches 2 of our function f of x. And again, that's the function that's graphed over here to the left. So again, if you like this idea of putting your left finger to the left of 2 on the graph, putting your right finger to the right of 2 on the graph, and moving your fingers closer and closer to that x value of 2, you'll notice that our fingers are definitely not coming together, and when they're not coming together to a particular value, and that value of course is a y value, we just report that answer as D and E. Please make a note on this one in that it's something that we're going to talk about only for this one moment, but it's not really something that's tested on the AP test. I think it's just worth talking about to again give you a better understanding of this idea of a limit. And it's something called oscillating behavior. As you know, sine, cosine, and the other trig functions are periodic. They repeat. And depending on the way a certain trig function is written, we can end up with pictures like this to the right, where we're taking this graph of sine of 1 over x and taking its limit as x approaches 0. Well, in this case, there's really no way for me to draw the fingers here, because you'll notice with this kind of really darkened in space here of the graph, what that's really saying is this graph is just going up and down, up and down, up and down, and up and down really, really fast in this tiny little space right here. And that's why it's called oscillating. When the graph bounces back and forth between two different values, up and down, -1 to 1, -1 to 1, since that pattern doesn't correspond to just one particular x value, we would say the limit as x approaches 0 again is D and E. If we're not approaching a particular value, we just say the limit does not exist. In this last case, you might be tempted to maybe say D and E, but we're going to use an idea that's been kind of touched on in your previous math classes, but is a tremendously big idea that we're going to use through the entirety of calculus, and that's the idea of infinity. In this last case, we're going to look at an infinite discontinuity. When the graph goes to infinity or negative infinity, maybe because of a vertical asymptote, that's when we're going to identify that as an infinite discontinuity. So if you take a look at the graph of 1 over x squared, which is graphed to the right, what this limit notation is saying is what's happening as we approach x equals 0. So again, if you like this idea of using your fingers, we're going to put our left finger to the left of 0 on the graph. We're going to put our right finger to the right of 0 on the graph. And as we move our fingers closer and closer to the x value of 0, you'll notice they're coming together in a sense. They're not going to quite touch, of course, because of this asymptote. But remember, we don't really care so much about that. We just want to know, is there a particular y value that as we're getting close to the x value of 0, are we approaching? And you can see, while it's not a particular x value, our left finger is going up forever to infinity. Our right finger is going up forever to infinity. And since both of those values, in a sense, correspond, we can report that as infinity. And here I'm just going to make the distinction that it's going to positive infinity. Since both of our fingers are going in the same direction, it's not necessarily that they're approaching the same y value, but since they're going in the same direction, and that direction is positive infinity, we can say this limit is equal to positive infinity. Of course, we can just flip this graph around and take the limit of negative 1 over x squared. The same idea applies here. As our left finger approaches 0 and as our right finger approaches 0, both of our fingers are going down forever towards negative infinity. So since both of those fingers are going towards the same direction, we can report that limit as negative infinity. So I hope really what you take away from this entire lesson is just the idea behind a limit, how to find a limit, and really the bottom line is that we're really just looking for a y value when we're trying to find a limit.